In this program, we are going to talk about time and distance. Distance has always been one of the major problems of astronomy, as we shall find out when we talk about it in the second part of the program. And timekeeping have always been functions of astronomy. For we get our time from the motions of some object in space. In most cases, that object is the Earth. You see, we live on our clock. Now, primitive man must have watched the sun rise and set and move across his sky for thousands of times before he had any conception that here was a cycle which he could use to measure an interval of time. It gave him that alternation of light and dark that we call the day. Now, we know that the sun does not actually move across the sky. We know that what we see is really a motion of the Earth, that the Earth is rotating from west to east with the sun fixed out here, and that as we ride around on the surface of the Earth, our horizon really falls away and lets us see the sun rising, and the horizon as we leave it comes up and makes the sun set. The motion is one of the Earth and not of the sun. And the day was undoubtedly the first natural divisions of time of which man became aware at all. Now, the day is a very convenient measure of time, but it has its limitations. How many days till your birthday? Well, you probably won't know unless your birthday is next week. But there is a need, and always has been, for a longer division of time, and that longer division, again, due to some motion of an object in space, was waiting there for man to discover. And that is the month. Now again, man in those far-off times must have watched the moon, thousands and thousands of nights, moving across the sky, and he must have been awestruck by its apparent change in shape as he watched it go. And it took him a long time, I'm quite sure, to realize that here again was another regular, constantly recurring cycle by which he could measure an interval of time. This month, this moon month, you see, moon and month must come from the same word root. This natural month is only 29 and a half days long. Now, 12 times 29 and a half is only 354. So the moon doesn't fit evenly into the year. And man tried to adjust himself to that condition by having an extra month every third year for a long, long time in order to make things come out right. And this year that we're talking about was surely the third natural division of time that man discovered, and that again is due to the motion of an object in space, this time to the motion of the Earth around the sun, the Earth's revolution. Now we know that the Earth is tipped from the vertical on its axis. And as we see it here, the tilt of that axis is such that the northern half of the Earth, on which we and on which our primitive ancestor lived, is tilted toward the sun. And that means that it's summertime up there. Now, in the spring and in the summer, things are growing. And primitive man ate, and so do we. But we have means of storing things up for the seasons in which things do not grow. And that happens 6 months later, when the motion of the Earth has brought it around until this time, the tilt of the Earth's axis brings its northern half away from the sun. And it's winter and cold, and things aren't growing, and primitive man went hungry. Now, the year to him was the year of the seasons that we have just seen. The year of the stomach, if you will, the year between hungers. And it probably wasn't until a great many of these years of the seasons had gone by that primitive man realized that there were, as he thought, 365 days between two successive hungry periods. Now we know from our ability to measure more accurately that the length of time it takes the Earth to make precisely one trip around the sun is 365 days, 5 hours, 48 minutes, and 46 seconds. But for thousands of years, men believed that it was an even 365 days. And of course that belief soon threw the calendar and the seasons out of step. And I suppose people began to celebrate spring holidays on the previous winter or something like that, until at last there was a man who had the knowledge and the authority to set things straight, and that man was Julius Caesar. Julius Caesar, with the help of some Roman astronomers, found that the year was 365 and a quarter days, as he thought. So, in order to set things right and bring the calendar back into step with the seasons, Caesar decreed, as he had the power to do, that the year that we call 46 BC should have 430 days. And it did, and it was known thereafter as the year of confusion. Now that put the calendar back in its place again. And in order to keep it there, and because Caesar believed that the year was 365 and a quarter days long, he said we can't add a quarter of a day to each year, but every 4 years we can pick up those quarters and have an extra day, which we will do. And Caesar invented leap year. Now, that was fine, except that we know from our knowledge that the year is actually 365 days, 5 hours, 48 minutes, and 46 seconds, as we said, that Caesar was 11 minutes and 14 seconds out of the way. By the year 1582, the situation had gotten so far astray the other way that Pope Gregory, one of the very influential men of the time, suggested another reform. He said, Caesar has given us too many leap years. We're falling behind. We have to eliminate some of these. And Pope Gregory produced a plan for eliminating 3 leap years in every 4 centuries. Gregory said, if the century year is divisible by 400, it shall be a leap year, but not otherwise. Now, that means that the year 1200 is a leap year. You can divide it evenly by 400. 1300, 1400, 1500 are not leap years. 1600 is a leap year. But 1700, 1800, and 1900 were not leap years. And the next century year that we have that is a leap year will be the year 2000. Now that is the calendar which we use today, the Gregorian calendar named after Gregory. But there are still 28 seconds a year that remain to be accounted for. Now that doesn't sound like very much, but you know, by 4500 AD, that will have added up to another day. And I suppose that 4,500 will be a leap year, although normally it should not be one. Now, there are the 3 natural units of time. We have talked about the day, which is the Earth, making one complete spin upon its axis. We have talked about the month, which is the moon, making one complete revolution about the Earth. We have talked about the year, which is the Earth, making one complete revolution about the sun. Now, man has taken these natural divisions of time and divided them up into smaller artificial time measures, hours and minutes and seconds. And here are some of the instruments that man used long ago to measure these smaller artificial time divisions. Here is a King Alfred candle whose alternating rings of white and black were supposed to burn each an hour, and which helped him keep track of the time. Here is an oil lamp whose reservoir held just enough oil to burn for 12 hours, and the passage of time could be gauged by the level of the oil remaining after a certain period of burning in that reservoir, as measured off on this metal band. And here, of course, is an hourglass, a sand glass, whose sand falls through it in a certain stated period of time. Now, we know that time is measured by the rotation of the Earth upon which we live. And we know that the Earth rotates in the direction that we call from west to east. Again, remember that the sun, to all intents and purposes, standing still out here, while the Earth is rotating around before it. So that our time comes to this part first, and then progressively moves westward. Time moves from west to east because the Earth moves from east to west. We know that the Earth's equator is a great circle. And we know, too, that all circles are measured off in degrees, and that every circle, no matter what its size, has 360 degrees. Now, if it takes the Earth 24 hours to make one complete turn, that carries us through 360 degrees, so that we move at the rate of 15 degrees an hour. And every hour, the Earth turns through 15 degrees of its own circumference. Knowing that, man has arbitrarily divided up the Earth into time zones, which are 15 degrees wide. And time is the same, simply by custom and agreement, all through one of these standard time zones. Actually, it isn't, because, of course, time must reach the eastern edge of a certain zone before it reaches the western one. But it's much more convenient to consider it that way. There are 5 of these time zones crossing the United States. And, of course, in these time zones, in different time zones, time is different. Here is a clock, which is set so that it registers 12 midnight at New York. Now, let's go around a little way, and we see that it is 5 o'clock the next morning in London. London has already had 5 hours time that we have not yet had. Astronomers have to use still another variety of time. Time relating to the stars, for that is where the main interest of astronomers lies. And again, that is caused by a motion of the Earth. Now, here is the Earth, and this little marker on it gives us an indication of how it turns, and let's say that you are the star. Now, as the Earth turns from west to east, it also moves in the same direction along its orbit around the sun. And as you can see, here comes our little marker again, facing you, the star, but this is before the Earth has made a complete rotation, a complete spin on its axis, so that the sidereal day is a little shorter than the civil day, the regular time day. There is a need for scientists, navigators, and the like to have a universal Earth time, and universal time is just what this is called. Universal time is time at the Greenwich meridian. The beginning of the point of measurement of distance east and west upon the Earth is also universal time, and all other time is related to that. Now, let us take a quick review of the 3 varieties of time that we have been talking about: civil time, universal time, sidereal time. Here are their hours. The sidereal hour, as you see, is a little shorter than the other 2. Here are their days. And again, the sidereal day is a little shorter than the civil day or the universal time day. Here are their years. But this time, the sidereal year is 1 day longer because of that little makeup of time each day that it picked up. Now, we've talked about the 3 natural measures of time: the day, motion of the Earth; the month, motion of the moon; the year, again, motion of the Earth. And time has overtaken us now, and we must consider that major problem of astronomy that we spoke about a little while ago: distance. It was all right for us to use the mile as long as we remained inside the solar system. It was a very convenient unit of measurement. But once we begin to leave that, we're in trouble if we still use the mile. For the very next object in space beyond the sun, the nearest star to the sun, is 26 trillion miles away. And I don't think anybody outside of the Treasury Department has any idea what a trillion of anything is. So, in order to accomplish these vast distances, we've got to use another measure. And we get that measure from the speed of light as light travels. Now, we know that light travels at the rate of 186,000 miles every second. That's about 7 times around the Earth at the equator every second. There are more than 31 million seconds in a year, so that the distance that light travels in a year is 5,880,000,000,000 miles. Now, at that distance, I think astronomy can be a little bit flexible. Call it around 6 trillion miles. That is a light year, the distance that light travels in a year at the rate of 186,000 miles a second. Now, on that same time scale, with that same speed of light, which is invariable, it takes light 1 1/3 seconds to reach us on the Earth from the moon. It takes light 8 1/3 minutes to reach us from the sun. It takes light 6 hours to reach us from Pluto, the most distant planet in the solar system, and it takes light 4 1/3 years to reach us from that nearest star I spoke of, Alpha Centauri. Now, how is man ever going to measure these tremendous distances, 4 1/3 light years? Well, the surveyors have taught us how to do that. A surveyor can measure the distance across a river or a lake without getting his feet wet. He does it this way. He sets up a marker on one side of the river across which he wishes to measure. Then he crosses the river again by any convenient bridge, doesn't matter where, and measures off a line whose distance he knows accurately. Then he sights back at his marker from first one end of the line and then at the other end, so that he has the angles from this end of the line to his marker and from this end of the line to his marker. Now, by trigonometry, if you have the length of one side and the angles at each end of that side of a triangle, you've got the triangle, and your surveyor has his distance that he wanted. The same thing can be done in astronomy. And we have set up a little experiment here in the studio to show you. Here are two spheres, this one and this one, and they represent two stars, this one far in the background, and this is the star in which we are interested and whose distance we want to measure. Now, we have arranged two television cameras standing side by side, focused upon these spheres. Now, we are going to see them first through the right-hand camera and see what happens. Now, do you see that the sphere, the front sphere, the one which is a plain color, is a little bit to the left of the rear sphere and against a different part of the studio background. Now let's look at them through the left-hand camera. Do you see how the plain sphere seems to be to the right and against a different part of the studio background? Now, we haven't moved these spheres. They are just seeming to move because we are looking at them from different angles. This is not real motion. This is a apparent motion. And again, our friends the Greeks had a wonderful word for this apparent motion. That is parallax, which means exactly that and nothing more, apparent motion. Now, how do we do this from the Earth with a star? Over here, we have a diagram which shows just what happens. We have to have a very long baseline on this triangle of ours because of the tremendous distances involved. So we start in by taking a picture of a star in the spring when the Earth is on this side of its orbit. 6 months later, in the fall, when the Earth is on the other side of its orbit, we take a picture of the same star. Now, in the first picture we took of this star, it seems to be against the background of these stars. In the second picture we took of this star, it has moved apparently to a background of these stars. There is your parallax. That star seemed to give a little jump in relation to the background stars. And the smaller that jump, the farther away the star is. Look at this one. Do you see, if we take a picture of this star first from this side of the Earth, it's here, apparently. If we take it again 6 months later, this star, it has only moved to here, and so on with one still farther away. Now, that parallax is measured in angles. And an angle, of course, is a division of a circle. You know what a right angle is. That measures 90 degrees in the circumference of a circle. And each degree of a circle is divided into smaller units of minutes, 60 minutes to a degree, and 60 seconds to a minute. Now, that means that there are well over 1 million seconds in the circumference of any circle, be it big or little. And the angle with which we are involved is on the circumference of an imaginary circle whose center is at this star and whose circumference passes through the two positions of the Earth. These angles are considerably less than 1/2 of arc, considerably less than 1/1,000,000th of the circumference of a circle. The very nearest star, that one we were speaking about, whose light takes 4 years and 4 months to reach us, has a displacement, a parallax of 3/4 of 1/2 of arc. So you can see how our neighboring stars can be the only ones involved in this kind of mechanical, mathematical measurement. Now, there is another quality of the stars which we can use to make measurements, and that is the star's brightness. Now, the word which astronomy uses for the brightness of a star is its magnitude. And in magnitudes, it's very much like a race. The brightest star is first, the next brightest second, and so on. There are 6 degrees of magnitudes, of course, with 5 intervals between. And they probably came from the old way of speaking of the brightness of stars. A star was very bright, the first magnitude. Bright, the second magnitude. Bright medium, third magnitude. Faint medium, fourth magnitude. Faint, fifth magnitude, and very faint, sixth magnitude. And the original astronomers said that there were 6 degrees of brightness which could be discerned by the naked eye. The 6th magnitude was the faintest star that could be seen without an instrument. There is an interval of about 2.5 steps between each magnitude. In other words, first magnitude is 2.5 times as bright as second, which is 2.5 times as bright as third, and so on. So that one first magnitude star, as you will see if you work it out, is equal to about 100 sixth magnitude stars. Now, what has this got to do with distance? Well, we know exactly how distance is affected, light rather, is affected by distance. Light diminishes by what we call the law of the inverse squares. In other words, if you get twice as far away from a light, that light will not look half as brilliant, but 1/4 as brilliant. Here is a little experiment that we have to show you what happens. Inside this box, as you can see, is a light source right here. Now, that is movable, you see. We can move it back and forth. And we have calibrated the lid of this box, which we shall have to put down now to shut out the studio light. Now, right here, at this first line, is our photoelectric cell. And here is the photometer that measures the light. Now, I'll turn the light on. Now, see, that measures at this point 16. Now, suppose I move this bulb, as you can see by the index here, twice as far away down to this line. What happens? It doesn't drop to 8, not to half of 16, but to 4. Do you see? 1/4 of the way. Now, suppose we move it twice as far away again, way down to this one. Watch what happens. It shouldn't be 2. It should be 1, and 1 it is. There you see it. That is the law of inverse squares. So, that if we know how bright a star is, we can tell its distance by how bright it looks to us. Now, how do we know how bright the stars are? Well, we can analyze the light of a star, and that will tell us just what elements are in that star and at what temperatures they are burning. So, by laboratory comparisons, we can tell pretty closely just how bright a star really is. Then the difference between how bright it really is and how bright it looks to us will give us a very good measure of its distance. And in order to facilitate this kind of comparison, astronomy has set all the stars at the same distance from the Earth, a distance of 32.6 light years. And the brightness of the stars, as they appear all at that distance, lined up in an imaginary fashion together, is called their absolute magnitude. Now, some of the more distant stars, which look very faint to us, would be brilliant giants at that distance, while our sun, which looks bright only because it is very near to us, would fade back to a kind of obscurity. The sun has an absolute magnitude which falls between 4 and 5. That means that it would just about be seen on a nice, clear, dark night if you had good eyes. There is still another way in which we must measure distance when we get out beyond the stars in our own star family, our local galaxy. Now, there are certain stars whose light is not constant. These are called variable stars. And one particular class of these stars whose light changes from time to time pulsate as they vary. They get big and bright and hot and small and faint and cool. And they do this with extreme regularity. There are many of these stars with different periods of variation, but each star sticks to his own time schedule. And the important thing about it is that we have found that the longer such a variable star takes to change from bright through faint and back to bright again, the brighter that star really is. There is a relation between the length of time the star takes and its real brightness. And we know that real brightness. So that when we see these pulsating stars, and we do see many of them in the most distant aggregations of stars, in clusters, and in distant galaxies far beyond our own star family in space, we can tell quite accurately the distance to these objects. Now, distance under these terms and at that scale can at best be an approximation. If we have come within 10% of the absolute accuracy, that's fine. If we get within 25%, that is acceptable. Time and distance are both overwhelming. And as one astronomer says, all science is simply an approximation of the truth. All man can do is to strive constantly to get closer and closer to the absolute truth.
This is National Educational Television.